Okay, in the last video, the last part, I had made a couple of mistakes on my notation. I went ahead and fixed that on this first part here. I just went back and looked at my work. Turns out, when I did this slide by slide, I didn't change my first couple of slides in this. So double check your notes if you're taking notes, and make sure that you yours reflect this. Now notice I did make one change to the sequence here. I started the sequence at 2. Now, see if this makes sense now. You take your first term and raise it to the first term in your sequence and raise it to the nth power to get whatever term you want. So in this case, since we know what the first terms are, we can actually be more specific than just g sub 1 raised to the n. We can say, okay, what is g sub 1? G sub 1 is the first term in our g sequence. And our first term in our g sequence is 2. So if we wanted to get the nth term of our g sequence, we take 2 and raise it to the nth power. If we wanted, let's say, the fifth term in our sequence here, we take 2 and raise it to the fifth power. So 2 to the fifth power, if you run to your calculators, would be 2 times 2 is 4, 8, 16, 32, I believe it is 64 at that point. Second, third, fourth, fifth. No, it's 32. Okay. All right, then we're talking about the Fibonacci sequence, and that's why I used F for my the name of my sequence here. Now, what about the explicit form of the Fibonacci sequence? Well, that is a lot harder than it actually sounds, and I'm going to leave that open for you guys as well. It's a little bit too hard for you to understand at this point, but kind of keep that in the back of your mind, because if we're just learning what explicit and recursive mean, then to put a nasty formula in here might be too much for you. That leaves the last sequence right here. And I'm going to do the same thing. Now, you might understand the pattern. There's actually a lot of different ways of understanding this last pattern. 1, 4, 9, 16, 25, and so on. Okay? But recursively speaking, it isn't that easy to build a formula out of it. And here's why. One way we can think of this, the pattern of this sequence, I know it stinks to give it away, but you can take between the first and the second term, you go up by 3. Between the second and the third, you go up by 5. Between the third and the fourth, you go up by 7. And as you can see, you're adding odd numbers in succession to go from one term to the next. Now, you might also notice, and if you notice this, great job, you're ahead of the game, that these are also the sequence of what we call the square numbers. To go from the term that you want to the actual term, so let's say you want the 7th term here, all you would have to do then is square the term you want. So in other words, squaring 7 gives me 49, so the 49th term, or sorry, the 7th term is 49. Hopefully that makes sense. Now, of all the sequences out there, there are two types that we care about the most. And the first one is called the arithmetic sequences. Okay? This one, in its purest form, this was the example that I had initially, was 1, 2, 3, 4, 5. Right? That very simply is an arithmetic sequence. There's another one. 2, 4, 6, 8. Okay? How about a little less obvious one? How about 1, 6, 11, 16, and 21? These are all arithmetic sequences. Now, what makes them an arithmetic sequence is that the difference between each term, the difference between 1 and 2, 2 and 3, 3 and 4, these are all constant. They are all constant term differences. Okay? Now, the easiest way to tell if something is arithmetic is to take two of the numbers in succession, find their difference, in this case it's 5, and then take two other sequential terms, so maybe 16 and 21, and double check that the difference between there is the same. In this case it is, it's 5, okay? And likewise the difference on this last term right here is 2, okay? So the common difference relates to each sequence. The common difference in this case, D, is equal to 1. Over here, D is equal to 5. And out down here, D is equal to 2. Okay. So all sequences that kind of go up or down by the same amount each time are called arithmetic sequences. Okay? And the recursive formula is pretty straightforward. All you do to get to the term you want is take the previous term and add the difference. So maybe we have, this is where it gets kind of messy. Let's say you have a sequence and you don't know what it looks like beforehand, but you do know that one of the terms is 7. And you want to find this next term here. Okay? You want to find this next term. Now, for whatever reason, they tell you, okay, by the way, the common difference is -3. Can you give me the next one? Well, hopefully. All you have to do is add the common difference to the previous term to get the next one. In this case, it would be adding -3 to get 4. I don't know what term we are here. Again, this dot 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 is kind of throwing me off. But I do know that if you give me the previous term and the common difference, I can tell you the next term. That's the benefit of the recursive formula. And it's kind of how we think about patterns in the first place. We say, okay, just look at the last one, and I can tell you what the next one is. Okay? So then, the explicit for arithmetic sequences is a little bit more complicated. Now, the benefit of this one, though, is you can get to any term you want. Okay? So, for example, let's do this sequence right here. Let's say we have a sequence that goes up by 4. Okay? Okay. And I want to know, for this question, I want to know the 17th iteration. I want to know what the 17th number is for this sequence. So in this case, n is equal to 17. So I want to find a, again I apologize for my handwriting here, but I want to find a sub 17. That's what I'm trying to find, the 17th number. Okay. Now, do we know what the common difference is? Do we know, for this problem, do we know what D is? Of course, D, in this case, is 4. Okay? 4. So that's going to be 4. And that right here, this n, is going to be 17. So far we've got 2 out of the 3 parts of this formula done. Now what we need to do is we need to add to it our 0th term. Now this is what I was saying before, that the 0th term is not part of the sequence. Okay? It's as if the sequence went backwards one step. To see backwards one step from what we already see. So this is the first term right here, the number 1 is the first term. But what would the 0th term be? Well, to go forward, we would add 4 each time. So to get the 0th term, we subtract 4. So 1 minus 4 is -3. Okay? So this number right here is -3. Hopefully that makes sense. So to get the 17th number, let's go through and in our calculator type this in. 17 times 4, well, let's see, 17 times 2 is 34, so double that to get 68, plus negative 3 gives us 65. And again, you can write this formula out, you can write this sequence out and hopefully get the same value I do. Okay? Hopefully that makes sense. We can do some more practice problems. Okay. Now, we talked about one type, that's arithmetic. Let's talk about the second type, which is geometric. So, a geometric sequence has a common ratio, meaning it goes up by a common rate. So, the example I gave you was 2, 4, 8, right? So, the rate in which it's growing is doubling, right? 2, 4, 8, 16. It doubles the previous number, okay, going up by a factor of 2, okay? You could do some other sequence here. You could do 3, let's say 9, 3 to 27, and so on. You could also, start with maybe 3 and go up by a common ratio of 4. So you go 3, 12, 48, and whatever 48 times 4 is. Okay? So the pattern with these guys, the pattern here is that we are multiplying by a set amount. Okay? In this case, we are multiplying by 3. We are multiplying by 4. Okay? So to get to the next term, you take the previous term and multiply by whatever the ratio is. So that's what we have for our recursive formula. Now, again, I use G to stand for geometric. Okay? For the geometric term, take the previous term, whatever iteration you want, go back one, and then multiply that number by your common ratio. So again, to get to the next term here, you're going to take the previous term, in which case is 27, and multiply it by 3 to get 81. Okay. That's using the recursive formula. Now, it's definitely going to be harder to use the explicit, but the explicit can be used. This one, you take your common ratio, raise it to the term power that you want, and multiply that by your initial value. So let's try an easier one here. Okay, let's say you've got 1 and 3 and 9. Okay, so again, it's kind of the same sequence we did before. It's just one step back now. Okay, now the pattern is you are multiplying by 3. So in this case, our R is 3. So let's say I wanted to find the, let's say the 7th term. Okay? I wanted to find the 7th term of this sequence. Okay. So then our n value, our n, is 7. So that n is essentially the number iteration that we want. Okay? However we want to think of it. 7. Okay. And then the last thing we would need to find in order to calculate this out is to find this this initial value. Oop, I want to do that. I want it black. Okay. There we go. Okay. We want this initial value. Now again, it's the 0th term. When I see 0, that is not going to be part of the sequence. It's as if we took the sequence and then went back one step. Okay? Now, this is where it might be very difficult. We have to go forward, we multiply by 3. So to go backwards, we are dividing by 3. So this guy is going to be 1/3. Okay? So this first term here is 1/3. Okay, so it's going to be 3 to the 7th power divided by 3. Let's see if this works here. And the final answer there is going to be 729. Okay? All right, for homework here. Try these out. This is the patterns that I want you to go through. Bring your questions for tomorrow.